Hey, computer scientists. So I told you I was going to come at you with one more piece of help for your interim assessment today, and I have got it. So I have in my hand very professional, artistic renditions of the five of the harder concepts that are on the interim assessment. And so I'm going to give you a little bit of visual for each one. And like I said, these are very professionally done. I spent a lot of time on these yesterday, so I want to make sure that you know guys appreciate them. So let's talk about concatenation. That's a big one, right? It's a big word. So let's pretend like each car in this picture is a string of characters, okay? And the guy in the middle is just there for comedic relief. So anytime you have two sets of strings, let's say it's like a big set and another set, and you concatenate them, and if you don't know what that means, check it out on Google. But when you concatenate them, you bring them together. If you don't know how to do it, check it on Google. I'm going to tell you what it is. So you bring them together, okay? But if we brought them together and there was nothing behind the car to start with and nothing behind the car to start with, and both of them backed into each other, there's no room for that little screaming guy in the middle, right? There's nothing in the middle. There's no data. There's no gap. There's no point in the middle. So by concatenating two objects, we bring them together and we make a single object, okay? Now, that's not like it is in the real world. In the real world, these two cars just crash. But if this was programming, this guy goes away. You can derive for yourself whatever you think happens to him. But these two cars come together and become one car, and that's what happens in programming. So a little different than the real world, right? Next. Really proud of these, by the way. Control flow. Control flow, that's a really good one. Now this, I'm extra proud of this drawing. I forgot to give him a face. But control flow, all right. So normally whenever this little dude, this little happy guy right here is pouring out his water, right? It's going in a straight path. It's just going straight down. Gravity is taking it and it's going, I don't know what he's standing on. He's kind of floating in the air, but he's pouring his water and it's just going down. However, if he introduced a few things into the path of the water, like this ramp right here, and then this curve, maybe it's a loop, so, and then maybe another curve, so he manipulates the path of the water. So now instead of just going straight down, it goes back, it goes to the left, goes to the right, and in this case it even goes back up a little bit, and then it goes back down. It's another ramp. Control flow. So control flow is how we as programmers can do that with our code. Normally our code runs from top to bottom, but by using different strategies like loops, while loops, do loops, all those cool things, and different kinds of functions, we can actually control the way that our code runs. So it doesn't just necessarily run down. It runs down, it stops for a minute, or maybe a long time, and then it keeps going, and then maybe even it goes back up and checks something up top, and it goes back down. So we can control the way that our program runs. I can't get it out. Whoop. All right. Object-oriented programming. Now, we just barely touched on object-oriented programming this year. We just barely hit on the surface of it. We'll be talking about it a little bit more because you're going to be building some objects in the next couple units. But this is the basics. If this is an object, right? Let's call it a Lego block. This is like a really tall, ugly Lego block. So this is your Lego block. This is your object. All right, this is the original object. Now, I'm going to call this the object builder. Now, normally we call this an object constructor, and it's a very special kind of function that allows you to build copies of objects, but we haven't learned that yet, so I'm just going to call it object builder. And by using this object builder, we can make tons of different pieces, bunches of different Lego pieces. Now, they could be the exact same as this one, or they could be a little bit different. They could have a different color, maybe they have a different number of holes on top, maybe they have a picture on them, but there's still instances of the original object, okay? So we have our original object, and then any copies of that we make for our code are called instances, and they're over here. So this is a really good one. I might keep these. I'm going to keep these for every semester. This is a good one, too. A lot of you have gotten this one confused. One of my most missed questions on IA2, and you're not going to miss it on the midterm. Arguments. So a lot of you know that an argument goes inside the parentheses at the end of a function, but you don't really know what its purpose is. Now, I don't know if this is going to make it any better for you, but I'm going to try it. So this looks like two equal guys arguing, okay? They're totally equal in their arguments, but they're not, okay? This guy has an advantage, right? Because he brought pre-made arguments. So this is kind of like how arguments work with a function. Some functions don't have any arguments, and we have to establish we have to put variables in them during the function. So while the function is being called, we have to establish certain variables that are going to be used, or we have to establish those variables within the function. But using arguments allows you to set a few variable values before the function gets ran. Okay, so by putting some presets inside of the parentheses and then just manipulating them inside the function, then it's much easier. It's much quicker, it's much more efficient, and it makes the function more flexible. It makes it to where we can use it in all different kinds of ways, and we don't have to use the same variable. For example, if you did a function that you wanted to add 1 plus 1, okay, and you did the function, and then you did no arguments, and you did function, and then under that you did 1 plus 1, or maybe you did x equals 1, y equals 1, x plus y equals, and then the function, and then return x plus y. Well, that would be 2, right? Your function would equal 2. The problem is you can only use that function now to add 1 and 1, and that's not very useful. However, if you put the x and the y inside your parentheses, inside your arguments, before the function is called, then you could run the function 1, 1, or you could run that function name 2, 2, or 2, 8 and get 4 or 10. So it's very powerful. Using arguments in functions. So try to remember that one. This is one I'm really proud of. I drew my bugs, my various little bugs. And there's a lot more bugs in programming than there is. We talked about a bunch of them this year, but these are the 3 of them that are maybe a little more confusing. So syntax. The syntax bug, he's pretty normal. All right, he's what you think of as your simple bug. He's your basic bug. But he likes, he gets a little faster, so he gets there quicker. He's the one that the code's going to find first. The debugger's going to find him first. And he's pretty easy to recognize, right? It's a grammar error, it's spelling error, it's an indentation error. It's things that are just obvious. These are like your ants, right? They're fast, but they're easy to kill, easy to get rid of, and they're usually the first ones you're going to take care of, okay? Because the first ones you're going to notice. Logic bug. These little, I call them devil bugs, and that's why he has horns and a pitchfork. Logic bugs are terrible. Logic bugs are the ones that will ruin your code, maybe shut down your computer, maybe break something. They're bad. These are endless loops, right? These are things that will crash Python completely and have to make you restart. So logic bugs are bad, and they usually have to do with control flow. It usually has to do with when you're trying to manipulate your control flow, but you're trying to do something that's outside of the capabilities of the program you're using. So those guys are bad. Conceptual bugs are just all confused, okay? See, he's got the right idea. His presentation is just not right. So he's got 6 legs, but they're all on one side. So conceptual bugs are a little bit different. Remember, conceptual bugs won't actually do anything to your code. They're just, your code will run. Your code will work just fine, but it just doesn't run the way that you want it to. So a good example of this, and this is the last thing I'll tell you, a good example of this is going to be if, let's say you have a program that you want to tell every time you eat an apple in your house, you hit a button and it subtracts the amount of apples. But what you don't realize is that it's actually adding 100th of an apple every single time. All right. So the problem is you're not going to notice this at all. And these are why conceptual bugs are so frustrating. Until you eat enough apples for that to show up. And if you don't have a round function, and some of these you don't know what I'm talking about, but if you don't have a round function in your program, and you eat by the time you eat 100 apples, it's actually going to look like you have one more apple than you do. And that's just going to stack up, and it's going to destroy, it's going to ruin your concept, what you want to do. So it works. It just doesn't work exactly the way you thought it was. That's a conceptual error. They're the hardest ones to find because often we overlook them as programmers because we run our code and we're like, yay, it works. And then we submit our projects. A lot of you have done this, and it's not working the way it's supposed to. So I hope those 5 little hints help you. Those are 5 of the more complicated concepts of the first semester. Next semester is going to be great. Good luck on your midterm, everyone. I will see you very soon next week for the last week of school. Bye.